the remaining section of momentum equation, momentum section, to finish up that chapter, momentum, and then we go to chapter number 5, the energy equation. Okay. Alright, so here we have this potential here. We have this control volume. It's a tanker, and initially we have water in it, and we have 2 inlet VB, VC, and then 1 outlet VB. Now you can see here this direction of flow here is because it's exposed to atmosphere. It's not very uniform. See that? It's chance. But in the question is they assume that this is constant, uniform, so approximately just 1 unit vector VD. So you don't need to do that integral, and then we have uniform EC, uniform VD, and there is no outlet. But one thing is important here is the weight of this water. So usually the problem is that are given to you, they assume that this point that all this inlet outlet, they convert this point is just tiny, a small fraction in the space, and there is no gravity, there is no body force. So they just totally ignore the hydrostatic weight of that object, that water. But in this question, you also need to include it on FED. So the way you draw FED, you just take this entire tanker as your control volume. So I saw some people, they took here from this part, right, this arm. But look, it's better to go all the way to the inlets and all the way go around it to the outlets. So that means that you also include the distance in your computation. Right? So what you need to do, just draw the borderline for your system, for control volume. Control volume is just the same old system one that we had before. So these are the borders. And we have one here. And then one here. You see that? So that's your borders. Now back to vector statics, when we wanted to draw a free body diagram, the first part of the question is just to draw the free body diagram, right? So if you want to draw the free body diagrams, what should I do? First, walk over this border, include all the surface force, and then include the body force. Right? So let's start from this point. You can walk either counterclockwise or clockwise. Right? So if I walk, I see that nothing is touching the system here, except here. Here, what do I have? You see, this is the cut section from the actual pipe. This is inside the pipe that is connected to the pump. You see that? So if I isolate that, what effect do I get from that pump? Pressure. The pressure. So the pressure, you put it here, and the force, the one you put on FED must be the force or moment, must be loading, back to vector extension. So the force coming from that is just pressure at B times area at B. So PB, AB, and it's this way. All right? Now what else do I have? Say it again?
The angle.
Yeah, but what else? Do I have extra loads here? This is the actual physical load, right? This is a physical load. What else do I have? The inertial load. That's the only thing we didn't have in vector statics, the inertial load. Why? Why we didn't have inertial load in vector statics?
Because nothing was moving.
Nothing was moving. Acceleration was 0. But here the flow is moving, it's coming in. Right? So inertial load, I know that it's m dot v, and it's a vector. So depending on the direction of v. And this is basically, you can write it as rho v times v dot n dA. That's, you remember in the double integral, surface integral, that tail? When you take it out of that, uniform v, you get times a. So you first do v dot n, and it's positive or negative, and then based on that, you find the direction of rho v square a, or m dot v. Right, so where is my n here? N is, let me draw n here. N is always pointing out. N is always like that. If I want to draw, you didn't have to do this in the midterm, but I just want to show you how it works. So n is always outward. So as you can see also here, n is this way. So if my velocity here, because it's coming in, right? Velocity is this way, is inlet. If I even don't draw that and I say this point is inlet, that means the velocity is coming in. So the velocity is going this way. And the normal is this way. So v dot n is what? It's a negative. So negative times this velocity. So the actual direction of m dot v, this force, is this way. Because v is this way, m dot, you do v dot n is negative, so it's this way, right? That m dot v. So when you put it on FVD, the inertial load, when you put it on FVD, what should you do with the sign?
Change it.
Just flip the sign. So you're gonna get, let me use green, dash, 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 dash. This is inertial, so that's the reason I use dash. And it's m dot at v, vb. Right? So, again, you do dot for dot. N is here, v is here, it's negative. The original v was this way. So, negative of this way, so the actual direction is this way. When you put on a v, just flip the sign. M dot v, vb. Don't forget this subscript, because later on when you put it in the equation, if you don't put subscript here, you're going to completely miss the values here. You may get confused with D or C. Right? So that's it. That's all the loading you have. Right? Continue working. Nothing. I'm not intersecting any external rear load, or no external fluid is leaving. Yes.
Why would you switch the direction of the inertial force on the FBA? If you're
Okay.
just gonna-
I think you already mentioned this. It's in the video. If you go back, I think it was 3 lectures ago. We had like a simple nozzle. Let me draw it here again. And if we have, let's say this A and this B. So BA and the fluid being BB, right? And if I draw the FBD only rear loads, you have an external reaction here to keep this nozzle in place, otherwise the nozzle will go right? So if I do the triple integral for that, you're going to get rho v plus rho v dv plus surface integral rho v v dot n dA is equal to sum of F external. This was the full momentum equation. The steady state, this is 0. So let's evaluate this integral. If I evaluate the integral, what do we get? We loop over here, 0 here, from here to here, we have what? Rho VA, right? V dot n is what here? Negative. Negative VA times AA. You agree? Do you agree with that? This just simply comes from here, this term. And then you go here, 0. What do we get here? Plus rho. That's the way it's incompressible. So rho everywhere is same. Rho VB, VB dot n. What do we get? Positive VB times AB. is equal to f external. What's f external? Negative f. So this is the, in the videos I said this is method number 1, the method that you both use. So he doesn't put inertial loads on the FED, he only puts actual physical external load, and then he uses this integral to come up with the balance, right? But look, if I do that, what do I get? If I bring everything to one side, what do I get? Take this to right, you get rho VA square AA, take it to the right. So negative becomes positive. Take this to the right, negative rho VB square AB minus F is equal to 0. We agree with that? That's exactly the same equation that comes from the triple integral, the double integral. Right? Do we agree with that? So look at it. If I do method number 2, instead of having this term come from the double integral, put it on FED. What direction should I use for that? Go to right, positive. But look, what's the actual direction of that? N is not here, right? V dot N is what? Negative. Negative from VA. So N dot A VA, the actual direction is here, negative. But you have to put it on FED on the opposite direction. So that's N dot A VA. Do you see that? So when you add it to the equation, you get positive. Do you see that? So positive here. What about this? This is actual direction in this way, right? Because N dot B is positive, so that's when N dot B VB. But when you put it on FED, the inertial load is going to be this way, M dot B VB. Now look at it. When you add this inertial load on FED, this one is positive, this one is negative, force is negative, is equal to 0. It becomes a vector-static problem. So just because of we want to convert the dynamics into vector static, did you have dynamics course? Yeah, when you take dynamics, they tell you whenever you want to put inertial load on the FED, when you have this load. All you need to do is just flip the sign. So the actual direction of inertial load that comes from the double integral, you just compute that and just flip the sign and put dash, dash, dash as inertial load. That's it. And what I recommend, if you want to really understand, the vector static part is okay, this book Keebler, but for dynamics, read this book. Dynamics. And he exactly explained how to transfer the initial load on FED. Which is basically, you don't need to memorize it, it's just the same thing. Every single time you do that, you find the actual direction, you flip the sign, put dash dash, and the FED. Just to convert this, which comes from double integral, to this. Because I took everything to the right. You see, when you take everything to the right, you just flip the sign. Now, the next boundary integral is this. So let me erase that. So you continue walking here. I need green. No external forces, then you come here. And you have another inlet. So here, what's the actual, first let's put actual physical load. The physical load here, again, you have a pressure at that. Let's put this point C, this is point B, and this is point D, right? And this is point A. Right? So you put actual pressure, which is PC, AC, and it's this way, it's a real load. What about inertial load? First find the direction of inertial load. Say it again.
The inertial itself would be pointing to the right.
That's right. First, you start with this equation. This gives you the actual direction, which is here. So you do V dot N. N is this way, V is this way, V dot N is negative times positive, so it's just opposite of that. This is the actual direction of actual inertial loop. But when you put it on FPD, you have to just flip the sign. So this is good. M dot C DC. Right? Don't forget that this is a vector. So that means it has y component. You see, this is a vector. This force has y component and x component, but pressure, it has y component, x component. This is not in the x direction. Well, and I'm glad I saw a lot of people give the correct way. So they decompose into x and y. Right? Now, continue walking here. There is no external load, no external load. Right? Then the next external thing is at the outlet. Should have put my fast forward again. The next external thing is right here, right? Do I have an actual force, pressure force?
No, because it's open to that.
Because it's open to atmosphere. The gauge pressure is 0. What about the inertial load?
Yes.
Yes. Let's compute the direction of the actual inertial load that comes from surface integral. It's what? V dot n is this way, times V is this way, right? So when you put it on a FPD, that means when you take everything to the right side to match it with some forces equal to 0, then you just flip the sign. So this is the direction of force. So the actual sign is on FPD this way. So you put it here. What should I put? What should I put there?
M dot D V
Yeah.
PD.
M dot D V D, and this is the vector. Right? So continue walking, and then you cut here, there is a picture, you actually fix it in point. Now, what I ask in the midterm is it gets X and Y. So you have two unknowns, assuming this pin, right? AX, AY. Assume this is a pin. But look, in the real life, if you build this huge anchor and just pin it here, just put a pin, and then turn on these pumps, what happens to this structure? Can you give me more precise? Let's say
It's going to rotate around
it's
A.
going to rotate. Do you feel that, the rotation?
Yes.
That will happen for sure. So what should I do at this point in order to prevent that rotation?
Set it.
Fix it, like weld it or put additional bolts, fix it to the, well, that is the actual thing here. You also have an MA, and I'm glad I saw many people also found MA, which I really didn't ask, so that's like extra credit. But look, right now, let's not concentrate on MA, let's concentrate on AX and Y, right? And continue walking, and then you're back to the start point. So you're gonna zip the entire control volume. So that's your surface force. What about body force?
The weight.
Do I have body force?
Yeah.
Well, you look at this and you say, well, how big is that? This is how big is this?
4 meters.
4 meters. Let me make sure. 4 meters right here. You see that? So that means from here to here is 2 meters. From here to here is 2 meters. And 2 meters is a little bit higher than my height. So this is just the diameter. So the base of this tanker is twice my height, approximately, more. And the height is 10 meters. 10 meters is almost like a 2-story building. So the weight, you can expect the weight is really significant. Weight is very significant. So I just put the gravity force you, so you can see, and weight. This is the weight of the object. Weight of the control volume, not the object. You don't have, I'm talking about the volume, control volume. So that's it. That's what I expect for you FPD, except this moment. Right? If you don't put a moment, that's fine. Because I said this pin. Right? Now, solution, the good thing about doing this all finding this and flipping the sun and all those extra work is the good thing is when you get that, you no longer need to deal with this guy. You don't need to do surface integral. You don't. Just consider this is a vector statics problem. You have bunch of fluids here. You see that? And then write equation of equilibrium. What's your equation of equilibrium? Sum of forces must be
Equal to zero.
zero, not MA, not acceleration, because you already included the acceleration on a field. Do you see that? And sum of moment should be equal to? Say? Zero, not I alpha. You remember dynamics? Which is basically the angular form of. Now your book has a different chapter for that, because what this author is trying to do is trying to make bigger book and make more money selling. But look, if you get this, you can also compute the moment. You don't need to have a separate chapter for angular momentum. It's just right there. Right? So now solution. Now let's temporarily turn this off, and we'll be back to it. One thing problem I have with this is it's very slow. It takes 2 minutes to turn on. All right, solution to that. You don't need this integral. Okay. Equation of equilibrium. How many systems do I have? So in fact, I'm doing this 5 steps. System, FPD, equation, solve, and then verify. I've done these two. Now, how many equations do I have? How many systems do I have? Let me ask. Do not say it, okay? How many systems do I have?
System?
I'm asking him, please.
Oh.
Yes. How many systems do I have?
2.
See, I've done this, and I've drawn my HPD. How many systems do I have, Jacob? How many systems do I have right here?
Wouldn't it be one system?
Just one system. It's just, you see, one control volume, one system. You see that? If you see another dashboard here, somewhere here, then you have 2 systems.
I was thinking about the streamline going from each one to the outlet, I think.
That's called a streamline. Now we come back to that soon, to the streamline, but I'm talking about this part of the step. So we only have one system, and we have one FPD. Now the question: how many equations do I have? Ask. How many equations do I get here?
3 different equations?
Yeah, 3 different equations. You don't get 6, you don't get 9. Why? Because you have one system in 2-dimensional space. One system gives you 3 equations, always. Alright? So let me write equations. Sum force makes 0. Sum force equals 0. Sum moment at any point, 0. Just like vector statics. You see, I converted dynamic problem to vector statics by putting initial load here. So on the right hand side, everything is 0. So let's do the first equation. So the first equation, because before I do the equation, I put the dimensions here. So from here to here is point. From here to here is 0.3 meter. From here to here is 10 minus 4, which is 6 meters. Then comes from here to here. And that distance is 10 minus 2, 8 meters. And here to here is 0.3. And here to here, again is 0.3. Now, bottom thing is the angle. So this angle, with respect to your x, is 20 degrees, and that's flat, right? This one is 45. This angle is 45. All right, now I'll just have basic vector static summation of forces x0. So you're going to get from this one, what do you get? M dot V, VD, right, times sine 45, and its value is negative. You go into that. Then you go to here, this is y, this is moment in x, you have positive ax. And then you go here, you have two forces, TA, PC, PCXD, plus M dot C, VC. Alright? And finally, here, again, you have combine these together, because both of them are force, so you can say P plus PB, AB, plus M dot AVB, times the entire thing times cosine 20, and it's positive.
Should be cosine 45.
Which one are you talking about?
M dot V, MD, VD, sine 45. You have sine instead of cosine. But
I mean, it doesn't matter. With
This
45.
one? No, it should be sine. You see? Cosine 45 give you this.
well, I'm looking at,
You're looking at the x. We're looking at the x.
yeah.
So you see, this one, sine 45. It gives you x. Look, it's very simple. Don't make it complicated. This is your vector, right? What's that angle? 45, right? So what do we get for x and y?
Oh, I see.
Which one is that and which one is this? Which one is this? Is this sine or cosine?
Sine.
Cosine.
I really didn't expect at all from you.
No, I'm being, I mean, you have cosine on your 20 here. I think it would.
Yeah, that is cosine. You see, this force times cosine, you get x. The other one is sine.
Okay.
But for that, you see, this one is cosine, this one is sine. I absolutely didn't expect that from you, but this is just a very basic.
It equals out to the same thing though, doesn't it?
No,
So-
let's say this was not 45.
Well, you have it drawn in a different place.
Yeah, well,
You have it drawn in a different place than it's drawn. Okay.
yeah.
You're right. You're right. I'm sorry. I'm
If
sorry.
this was, let's say
I
this,
drew it on the other
Yeah.
angle. So.
we're good. If this was not 45 or 26,
Yeah,
for
it would
example,
make a difference.
you have to really go through the right procedure. You can't just say, well, this axis will be cancelled out, yes, because they're 45. But you have to really do the right thing. The right thinking, the right formula, the right. That's the way of grading. That's the way of grading. And we have a student getting 100, and we have a student getting 5 out of 100. It's because of things like that, right? So, plus that times cosine 20 is equal to 0. So that's the first equation. The second equation, sum force in y, starting with that, you get m dot d dd sine, cosine 45, and this one is positive. And then you go to these guys, and in the y, you only have plus ay. And then this guy doesn't have any y contribution, and this guy is simply put both of them together. There are 2 forces plus PB, AB plus and B, VB. That's the sum of these 2 forces. Now you want to get the y component. You do sine 20. Positive or negative? Positive, go up. What else you have?
Weight,
That's a very, very important. And you realize if you forget the weight, your result in the y direction, in x your result is perfectly fine. In the y direction your result is off by 2 orders of magnitude. So negative W is equal to U. And some moment about any point must be 0. Now I saw some students they wrote this. Now I want to also, for the purpose of being complete, I want to also write that and point out a couple moments here. Which you didn't have to do that, but I want to do it. So with respect to any point, I just put some A is equal to 0. And let's go step by step, find the moments. So starting with this guy, break it down. So if you break it down, you get y and x. So let's first work with the x component. If I move this here to get the moment, how much is this distance from here to here? Can you tell me? 6 minus?
6 minus 0.3.
Uh-huh. Is that right?
1.3 times sine of 45. Or cosine, sorry.
Yeah. 0.3 times cosine. Can you? Another quiz waiver. I haven't applied your previous quiz waiver. Right. 0.3 times cosine 45. So look, it's 0.3 from here to here. You see from this tip. If you want to get from here to here, you just project that into here. So 0.3 times cosine 45. It's from here to here. You see that? It's from here to here, that distance. 0.3, which is from here to here, times cosine 45. Now, if you want to get from base all the way to here, you have to subtract the 6. So 6 minus 0.3, cosine 45. That's your moment arc. It's multiplied by the force. What's the force in the x? We just had it. What's the force when we ask? What is the component of x direction of that force?
Repeat your question, of what force?
What is the x component of this force? The initial load here, that I'm trying to get them all.
It would be sine of 45 would be what you're getting at, so it would be
So this moment arm times?
times MD
Uh-huh.
VD
And
sine
what?
of 45.
D, VD, sine 45. Thank you. So positive or negative?
That would be positive.
Positive, because it's going up.
Counterclockwise
Yeah.
rotation.
Yeah, that's going to be positive. So this is in fact multiplication. So the entire thing is positive. All right, next one. Next one is you get, this was the x, you get the y component. So what's the y component? And I'm going to write it here. I really wish we had a bigger whiteboard. Plus, yeah, let's write it here. Dot, dot, dot. So I write the next one here. So the y component is m dot v vd cosine 45, right? Which is distance. So I want to find the moment with respect to that. I move it down. So what's my moment arc?
It would be 2
Uh-huh.
plus 0.3 sine of 45.
Yeah, sine, thank you. 45. Positive or negative?
Positive.
It is actually positive because the y component are this way, it's going up. You just move it down, right? So that's done with this. Then I go here. What do I get from AX? Let me ask you not say. What contribution do I get from AX?
0.
Thank you. what do I get from AY? What do I get from AY?
Just look at AY, correct?
With respect to this point.
Oh, with respect to,
You
Zero.
see, my reference point is A.
okay, I
It's
got you, zero.
Thank you. And what do I get from MA? Just MA. Do I have it? No, I just put MA. Positive or negative?
Positive.
Right? Now, what do I get from weight?
Zero.
Zero, it passing through that. Right? Now, come here. What about the moment generated by that with respect to that point? Do you see that? What should I do? I'll move it all the way here, right? So the moment on is from here to here. How much is that?
8.
8. So you say 8. So dot, 8 times. Now combine this together. So PCAC plus M dot CVC. Put it together. M dot CVC plus PCAC. So 4 times. One more time. Positive or negative?
Negative.
Am I done?
No.
The last thing, this guy. Now again, put these two guys together, combine it, because you can do it separately, right? Or just take some of these, because you don't want to repeat the cosine 20, sine 20 like 4 times. You just do it 1 time. So PA, what is my x component? Because I need to get x, move it to the right, this is my momentum, and then I need to get my y and move it down, and this is my momentum. Basic, simple vector statics problem. So here, what do I get for x?
Be cosine.
Yeah. So m dot b vb times plus pb ab. This is the your force, the net force. Then cosine. Say that again. Cosine 20. So that's your x. Now you move it all the way to here, right? So what's my momentum? Let me ask. Everybody, what's the momentum? The x component. You see, you get the x component. You move it all the way to here. What's the momentum?
Is that distance 3? 8.
Yeah, it's 3.
Is that the 3?
This.
It's 3 meters to the middle of the.
Yeah.
Minus
So the center here, from here to here, is what? Do you have that distance?
3 meters.
That distance is 3. Let me double check. Hopefully I don't have to log in. Yeah.
sine of 1.
So this is from here to here is 3. But look, this force is not here. This force is here. Do you see that? So if I move this here, you see that? Then is that 3? The momentum is not 3. It's smaller than 3. How small is it? Yeah. So you say that force cosine 20 times 3 minus 0.3 sine 20. All right. Positive or negative?
Negative.
You get negative. Now, am I done? Let me ask. Emily, am I done? What is missing from right region? The moment of region. Please do not say it. You see, I'm asking everything. You see, this is my force. I project it into x, which is the sum of these two, times cosine 20. And then I move it all the way to here. So with respect to that, it's 3 minus 0.3 sine 20. So that's a moment comes only from x component. Is that what I have?
You need the y component.
Yeah, you need the y component. That's the answer to that. So y component, what's the y component? M dot, the same thing. So I'm going to write it here. M dot b, bb plus P AB times sine 20, that's your y component, and it's going up, right? It's this way. But look, at this point, all you need to do with respect to that to bring it down, so your moment arm is from all the way from here to here. So how much is your moment arm? From here to here is what? 2 meters plus 0.3 cosine 20 degree. Positive or negative?
Negative.
Yep, it's because it goes out here, when you move it down, R cross F is negative. What else? That's all, right? This sum must equal to 0. So this is a very long equation, as you can see. It's just one single equation. And that's the reason I didn't ask you to do that in the midterm, because it's a little bit long. It's optional. But I saw some students did it. Yeah.
If this was a real object, could we just do the MB or MBVD P and A, and then just measure like how far it is perpendicularly, and not have to do that as a mode?
Yeah. So that's actually the way you do that. You locate this inlet, right? This is the inlet. You locate that and you measure this R. So you have. That's the reason I give you all this measurement, because you can quickly measure it with a meter stick. All this. So that you have 3 equations. Look, 1 equation, 2 equations, and 3 equations. And what I asked in the midterm was this. Why? Because from these 2 equations, you get AX and AY. If you have the rest of it, right? You just substitute there, and you get AX and AY. Well, look, what do I need in order to compute that equation?
Pressure.
You need pressure, let's write it here.
M dot
You
B,
need
Velocity.
P at C, you need P at
B.
B, you need velocity at the out, here, B.
Yeah.
And we know that velocity at these 2 points are given. Can you verify? I think the velocity here was 2, this one was 1.
yes.
Is that right? So you already have VB 2 meter per second and VC 1 meter per second. Right? So what you need to find VDY, because this equation has VD in it, right, for Y. You need to find VD, and then also you need to find all the M dots. M dot C, M dot B, and M dot B. What else do you need? The weight. Right? So I'm going to find this. But look, if I want to find, this is what I expected you to do. If I want to find velocity here, what should I do? In the appendix, I have 3 equations: conservation of mass, Bernoulli, conservation of momentum. Which one are you going to use? Conservation of mass. If you want to find the velocity here. We're not done yet. We still have 4 minutes. So if you want to find velocity here, you use conservation of mass, which is basically, I'm not going to write the integrals. It's going to be m dot a. That one is what? M dot b negative m dot c plus m dot d is equal to 0. Now what's m dot? Negative rho b, vb, ab, negative rho c, bc, ac, plus rho b, vb, ab is equal to 0. Look, in compressible, all the densities are same. So they cancel out. So your vb is what? Your vb becomes, take this to the right, so you get vb, ab, plus vc, ac, divided by ad. Substitute numbers here, BB is what? 2 times AD pi, the radius. What's the radius here?
0.2.
Is that the diameter or radius?
B.1 is the radius.
So let's write in here, RB is what? RB is 0.1 meter, is that right? Is that right? Okay. What about RC?
0.25.
0.025. What about RA? RB?
0.075.
0.075? I'm not sure if this is right. Is that right?
Yeah.
Okay. Alright, so plug in the numbers here. So you have 2 RB. So you have 2 times pi 0.1 square plus VC 1 times pi RC squared divided by pi times RD squared. So you solve that. You get BD. Alright? So I get BD. How do you find? So put it here. You get that. How do you find M dot C? M dot C is simply rho times BC times AC. So it's 1000 times BC, which is 1 times AC pi RC squared. All of it you have it. M dot A, there is one. M dot B is equal to 1000 times BB, 2 times AD, which is pi RB 0.1 squared. So you get that. M dot B again is 1000 times velocity at D, which comes from here. So you put this velocity here, times pi 0.075 squared. So you get all of these M dots by number substitution. And what about weight?
Rho VG.
Yeah, so weight is what? Rho V times G. So you have here, mass is what? Density is mass per volume. Therefore, mass is rho V. You multiply by G, so you have rho V times G. So rho is 1000 times pi, the radius, which is 2 meters, the radius of the tanker. Is that 2? Can't see it.
For the tanker will be 2.
Yeah,
The diameter was 4.
yeah. 2 squared times the height 10. So you get that. What about PB and PA, PC? These two? The only thing remains is PC. Right? If you have that, you just get the value. Now, this is the thing. If you write Bernoulli equation between C and B, that is not right. Why?
Because that's
That's right. Because you see, when we draw, that's the reason why I said you have to learn the proofs, the derivation. When we drive the Bernoulli out of the momentum equation, we did the line integral. Over what? Over what we did the line integral? The string line. Can you tell me there is a string line between these two? There is no way. All the flow goes this way, this way. Some of them, they may come here and get trapped, but they never go this way. There is no way. So Bernoulli equation, so you write Bernoulli equation between these 2 points. Let's do that. We finish next time.